And feel free to stop this at any time because I'm just going to be flying through it, and that way you can pause it and write down the notes as you go along. First of all, Newton's first law says that objects at rest stay at rest. Objects in motion stay in motion in a straight line and at the same speed unless an outside force comes along and acts on them. And the demonstration we're going to do in class is both the tablecloth trick and also a little hovercraft that we're going to float down the hallway. Now, next you have Newton's second law, and what that says is that force is directly proportional to acceleration. In other words, if you put more force on an object, you're going to accelerate faster. Now, it also says this: the heavier you are, the more massive you are, that's inversely proportional to acceleration. Now, what inversely proportional means is one thing goes up, the other thing goes down. So the formula we're going to have for this particular law is F equals ma, where F is the force, m is the mass, and a is acceleration. You could also say that a equals F over m. So once again, if force increases, acceleration increases. If mass increases, acceleration decreases, because they're inversely proportional. And the great example I usually use, if you're at a stoplight, you would pull behind a sports car instead of a semi-truck, because the car has less mass and much greater acceleration. For Newton's third law, for every action there must be an equal and opposite reaction. So the example that we're going to do in class is I'm going to have one scale, or actually two scales. One person's going to push a scale to the right, the other one's going to push on it to the left, and you'll notice that the scales are always equal. But just like last chapter, whenever we had the metric unit for mass, we used a kilogram. But now there's going to be a different metric unit for force or weight, and that is a Newton. So we could also say that instead of saying weight there, you could also put the word force right above the word weight. And I have a very, very lousy stylus, so pardon my poor handwriting. So you might remember that old Fig Newton commercial. It is not a cookie, it is a fruit cake. Well, anyway, if you eat too many Fig Newtons, you add a lot of weight. So therefore, weight and Newtons, or Newtons are the unit for weight. Number 6, suppose a car is being moved by a certain force. If the net force is doubled, well, how much will the cart's acceleration change? Well, if it's directly proportional, if you double the force, you will double the acceleration. It's sort of the same, the inverse happens with the mass, though. If you double the mass of the car, now your acceleration will go down by half. Because remember how we said it was inversely proportional? Well, that means if you double the mass, the inverse of 2 is 1 over 2. So that's why the acceleration would be 1/2. Going on to number 8. Got this pretty big problem here. Got a 50-gram tennis ball. So let's give me some room to write here and work out this problem. Okay, let me erase this here. Okay. There we go. All right, so the first thing it says, we got a 50-gram tennis ball. Well, guys, you can never use grams in a formula, so we got to change grams to kilograms. If you remember when you did that, you put the unit you're given at the very beginning, so I got 50 grams. Then you put that unit on the bottom to cancel it out. I know how to go from grams to kilograms. You put a 1 next to the prefix unit. And since kilo means 1,000, you put 1,000 on the bottom. So that means that 50 grams is 0.05 kilograms. Now, since the tennis ball is served and accelerates from rest, that means its original velocity is 0 to a speed of 50 meters per second. So that's the final velocity right there. So we can write those down over here. The initial velocity is 0. The final velocity is 50 meters per second, and it does that in a time of 0.9 seconds. It says, what is the force on the ball? Well, the formula we just looked at up in the equations there was this little new triangle that you got, that force equals mass times acceleration. So I'm just going to put down F equals ma. Well, my mass is calculated to be 0.05. Now, I wasn't given the acceleration. So whenever you don't know something, you've got to plug in another formula you know. Well, I do know that acceleration is delta V over delta T. And so now I'm going to put in the change in velocity, which is final, which is 50, minus the initial velocity, which is 0, all over 0.9. And when you come up with the answer there, so that gives you the answer of 2.78. Now, the mass would be measured in kilograms, and the acceleration would be measured in meters per second squared. But the actual unit for force is newtons. So we can also say it's 2.78 newtons. Let's take a gander now at number 9. It says using the concepts of inertia and force of gravity for both a coin and a feather, explain why both will fall at the same rate. And I'm going to show you a vacuum tube. I'm going to take the air out of it, and you'll see that a penny and a feather will fall at the same rate. But let's discuss why based on inertia. If you look at these three things, when you look at the coin has a lot more mass than the feather does. Well, if you have more mass, that means you also have more inertia. So if you're at rest, you want to stay at rest. So the coin wants to stay at rest, so it's going to start off real slow. But the feather, on the other hand, has less mass, so it has less inertia. So it doesn't want to stay at rest, so it's going to start fast. But look what force does. The coin also weighs more, so with more weight, you have more force on it. Well, that makes it want to start off faster. But the feather has less force. So if you have less force, that means you have less weight. And so that means you want to start slower. Well, think about it. Look at this. I got slow over here on the inertia side, fast over here on the force side. Slow plus fast equals sort of medium of 9.8. But the feather wants to start fast, but because of its less inertia, but it wants to start slow because it has less weight. So fast plus slow equals a medium of 9.8. So everything falls at 9.8 meters per second squared. Sort of explain that. Inertia and force balance each other out, and they create an equal acceleration. Now, if you look at these formulas I have written down here in big letters and little letters, if you take a big force and you divide it by a big mass, you get the same number. For instance, 10 divided by 10 over here. 10 divided by 10 is 1. Over here, I have little letters, little f divided by little m. Well, if you take a little force like 1 and you divide it by a little mass like 1, you still get 1. So once again, inertia and force are constantly balancing each other out. So if you have a big force, you also have a big mass. If you have a little weight or a little force, you also have a little mass. So the ratio of acceleration is always the same of 1 meter per second squared. So let's take a look at this. At terminal velocity, now terminal velocity is when a skydiver is dropping out of an airplane, let's say, and you would think that he keeps speeding up and speeding up. Well, eventually he doesn't, because the weight of his weight going down, so I'm going to call this the force of his weight, will eventually equal the weight of the air pushing up. So this is the force of the air, otherwise known as fair. And if those two things equal, you get a net force. Now, the sum of all the forces, is what's that little sigma, would end up being 0. Well, if you don't have any force, you don't have any acceleration. That doesn't mean you don't have speed. That just means you don't have any acceleration. So look at this. It says at terminal velocity, a 120 kilogram skydiver is falling at a constant rate of 30 meters per second. What is the force of air resistance? Well, if the force of the man is his mass times acceleration, you got to remember his mass was 120. See, I got 120 kilograms there, times his acceleration of 9.8 meters per second squared. That gives you 1,076 newtons. Well, if his weight was 1,076 newtons, that means the force of air going up must be 1,076 newtons. So actually the weight would be a negative 1,076 because it's going down. and the force of air would be a positive 1,076 because it's going up. Okay? So four forces have to be equal and opposite. You look at number 11 now. What quantity is the measure of inertia? It's mass. Let's keep going on to the next one. And it says, considering the definition and not the formula, what's the difference between mass and weight, and which is dependent on the location of the object and why? And then you had to explain why are astronauts weightless in orbit, and use the falling water bottle to explain your answer. Well, first of all, mass is the measure of the amount of matter an object has, and it doesn't change with location. So if I was going to shoot up to the moon, now I might get scared and lose a little bit of mass, if you know what I'm talking about there. But for the most part, my body mass is going to stay the same. But since the moon is not as big as the Earth, it doesn't pull on me as much. So since its gravity is less, I don't weigh as much on the moon, even though I have the same amount of mass. Now here's the reason why astronauts are weightless because when they're falling around the Earth, it's because there's no support force. Let me get a little bit more room to write here. First of all, you got to understand why you feel weight. And yes, weight is the force of gravity pushing down, but you only feel it because the Earth pushes back up on you as a reaction force. Okay? So you feel the Earth pushing back up. You don't actually feel gravity pushing down. So let's say I got my Earth right here. There's Earth. Wow, that's a nice circle, Jeff. Good job. So there's Earth. I'm going to have a little space shuttle flying around Earth, or it could be a sock. Shoot. Now, once you get the space shuttle up in the air, they turn off the engines. And due to inertia makes the space shuttle want to go out in a straight line because objects in motion stay in motion in a straight line. But gravity pulls the space station down, and you would think there wouldn't be any gravity out in space, but there's a lot of gravity out in space. In fact, I think it's almost 90% of the same gravity we have down here. But the thing is, when gravity pulls the space station back down, look what happened to the surface of the Earth. The surface of the Earth actually curved down a little bit. So therefore, when the shuttle starts to fall, the shuttle now comes over here, okay, in a straight line. Now, inertia makes the shuttle want to go out again in a straight line. But what does gravity do? It pulls it back, okay? But now the Earth's surface curved down again. So if you notice, the space shuttle is always staying the same distance off the surface of the Earth, okay? Every time it tries to fall, the Earth's surface curves down, and so therefore, the space station is actually falling around the Earth. Well, if you're falling around the Earth, then you have no support force. The Earth can't push back up on you. And that is why you are weightless. So it's not because there's no gravity. There's lots of gravity. It's because the Earth can't push back up on you. So you are weightless because there is no support force pushing back up on you. So what's really sweet about this is the fact that we can put a space station up there without any fuel at all. It just keeps going around the Earth, keeps falling around the Earth forever. And if we want to bring it back down, all we have to do is slow the thing down. As soon as you slow it down, it's not going 18,000 miles per hour anymore, then it just simply falls back to Earth. Okay, let's look at number 13 now. It says, how much mass does a person have? That's 100 kilograms. Well, guys, don't even do any equation yet, because all you have to do is look at where it says mass, because mass never ever changes. So where it says 100 kilograms right here, a 100 kilogram person is always going to be a 100 kilogram person, whether they're on the moon or on Earth. 13b, though, it says how much weight does it have? Well, you got to remember that we started off with the formula F equals m times a, and a is the acceleration due to gravity. So my mass is 100 kilograms, my gravity is 9.8, and so that gives me 980 newtons on Earth. But I don't know why I put 9.8 there, because we're looking for the moon's acceleration. So let me do this over again. I'm going to take 100 times the moon's acceleration due to gravity, which is 1.8. I even think that's 1.6 really. And so that gives you 180 newtons that you would weigh on the moon. So if you want to lose weight, heck, don't do all the workout and stuff like that. Don't stop eating. Just go to the moon. Number 14, when you walk, what causes you to go forward? Well, this is a little bit strange because you got to remember Newton's third law. For every action, there's an equal and opposite reaction. So your foot pushes backward on the floor. You push backward, but that's not what makes you go forward. It's the floor that pushes you forward. So your reaction force pushes you forward. Same thing in a tug-of-war match. When one team pulls on the second team and the second team has an equal and opposite pull on the first team, it seems like, well, heck, there's no way for a team to ever win. Well, it's not who pulls on the rope the hardest, it's who pushes on the ground the hardest. Because if I want to win a tug-of-war match, I push forward on the ground, and the ground pushes me back. Well, if I push harder forward on the ground than the other team does, then I'm going to be pushed by the earth backward more than the other team is, and so therefore I will push them in the big mud pit. So number 16, all these are Newton's third law questions. Number 16 says, when a hammer hits a nail, which delivers a greater force, the hammer on the nail, the nail on the hammer? Absolutely equal, because Newton's third law says for every action there's an equal and opposite reaction. So since the hammer's force has to equal the nail's force, then the mass times acceleration of the hammer has to equal the mass times acceleration of the nail. So the nail has less mass, so it must have greater acceleration. So let me write this down up here real quick. Let's just look at this MA. Let's just say the hammer had a mass of 1,000 grams, and you accelerated it 1 meter per second squared. Well, if you hit a little nail, a nail might only have a mass of 1 gram. Well, for those two things to be equal, look what the nail has to do. It has to accelerate at 1,000 meters per second squared. And that's why the nail goes into the wood, because it's accelerating so quickly. Okay? But they both have the same force on them. Number 17 is very similar to that. When you jump up on the earth, does the earth move downward? Sure it does. But you can't notice this because the earth is so big. So the same thing happens here. Let's say that you have a mass of 1. Okay? And you have an acceleration of, I don't know, of 10. Okay? Well, the Earth's mass is, I don't know, 1 billion to 1 trillion times bigger than you are. So therefore, if it has a huge mass, let's say it has a mass of 1,000 or whatever, 10,000, that means it's only going to accelerate at, 1,000th of that. So it'd be 0.001. And so you can't hardly notice that whatsoever. I just made those numbers up. So the bigger mass you have, the less acceleration you're going to have. I'm going to erase that because that's confusing. All right. Number 18. How can a rocket be propelled above the atmosphere where there's no air to push against? Well, guys, the rocket doesn't push against the Earth. The rocket doesn't push against the air. It's the fuel in the rocket that pushes against itself. So let's talk about what happens here. Okay, well, here's your rocket, okay, and you got some red or blue fuel in here. Okay. Well, what happens is the action is the rocket pushes the fuel down. Okay. Well, the reaction, you simply say it backwards. The fuel pushes the rocket up. So you don't see anything about the earth there. You don't see anything about the air there. It's just the rocket pushes the fuel pushes the rocket. So when you're in outer space, you don't need any air. You don't need an earth to push against. It's just the two things connected to each other that are pushing equal and opposite directions. Let's talk about this horse. You got a horse pushing on a cart, and the cart pulls back equally on the horse. How the heck can the horse ever move the cart? Because they're canceling each other out. Well, it's not the horse on the cart and the cart on the horse that make any difference at all. It's how much the horse pushes on the ground. So if the horse pushes back on the ground, what happens? The ground pushes the horse forward. And as long as the horse pushes back on the ground more than the cart pushes the horse backwards, then, by golly, they're going to go forward. And lastly but not leastly, if you flip a coin above your head while you're in a bus that's moving 40 miles an hour, where's the coin going to land? Well, you got to remember the coin's also going 40 miles an hour. Even though you're in the bus and it looks like it's sitting still, then the inertia of the coin makes it want to keep moving at the same speed. So when you flip it above your head, you shouldn't say above your head, but when you flip it in your hand and it goes above your head, it will land back in your hand because inertia is moving the same speed of the car. All right, thanks again for writing down all these notes. We'll do a bunch of demonstrations in class, and that way you don't have to write them down as you're trying to watch the demonstrations. Hope you have a great day. Thanks a lot. Bye.